Have you ever found yourself looking at an automated decision?
You mean like maybe a loan application gets rejected?
Yeah, exactly. Or
Yeah.
maybe a rental approval or even a medical diagnosis from an AI.
And you're just left wondering, well, why?
Right. Because AI systems, I mean, they're so woven into our lives now,
They really are everywhere.
making these, really complex, impactful choices.
And yeah, often those decisions feel like a complete black box. You just don't know what went into it.
It's unsettling.
Yeah,
And that lack of clarity, well, that's why our deep dive today is so important, I think.
absolutely. We're going to try and unpack how we understand these systems.
We are. Today, we're cutting through some of the jargon, hopefully, and getting into a fascinating new report from NIST, the National Institute of Standards and Technology.
That's right. It's NIST 8367. It's called Psychological Foundations of Explainability and Interpretability in Artificial Intelligence. Quite a mouthful.
It is. But our mission here is to really understand what explainability and interpretability actually mean for AI.
And crucially, why knowing the difference between them is so fundamental, not just for developers, but for all of us.
And it feels really urgent right now, doesn't it? This isn't just some abstract tech challenge.
Not at all. It's policy, it's ethics, it affects millions.
Think about laws like the Equal Credit Opportunity Act here in the U.S. or GDPR over in the EU.
Right. Those laws are now explicitly requiring AI systems to give explanations or interpretations to users.
Which directly impacts people, potentially vulnerable groups even. So yeah, this conversation needs to happen now.
Exactly. There's this growing demand from society, really, for transparency, accountability.
We want to know why the AI decided what it did, not just what it decided.
Okay, so let's dive straight into the core of this report then. Let's unpack these concepts. Interpretability versus explainability.
Yeah, because it seems like people use them interchangeably all the time, even computer scientists.
Except they do, and it causes a lot of confusion. But this NIST report argues, quite strongly actually, that they are fundamentally different psychological processes.
Okay, so that's the starting point. Let's break them down. Where do we start? Interpretability.
Let's start with interpretability. So, for us as humans, interpretation is basically our ability to make sense of something.
Like an AI's output.
Exactly. To derive meaning from it, so we can then make a decision based on that meaning.
Okay. And how does that work? The report mentions something about gist representations.
Yes, just representations. I like that term too. It's about creating these simple but meaningful mental shortcuts.
So not all the technical nitty-gritty, but the essence, the bottom line.
Precisely. The gist contextualizes the AI's output using your own background knowledge, your values, your goals.
Ah, okay. So an interpretable model gives you what the output means in context.
Exactly. It gives you insight, helps you make that high-level decision. Think of it as getting the why in a way that's actually meaningful and useful to you.
Okay, that makes sense for interpretability, meaning context, the why for the user. So then explainability, why do we need that too?
That's a great question. If interpretability gives you the meaning, what's left? Well, explainability shifts the focus entirely to the how.
The how, as in how the model actually works internally.
Yes. Explanations are detailed descriptions of the mechanisms, the nuts and bolts, how the outcome came about, focusing on the specific process or the rules the AI followed.
Right, so this sounds much more technical, not really for the average person getting a loan decision.
Generally, no. It's more for the developers, the engineers, the auditors, maybe. People who need to look under the hood.
To debug things.
Sure.
Or improve the system.
Exactly. Explanations are detailed. Sometimes they get into the causal steps, though that's tricky. They aim to describe the process that generated the output, kind of independent of the wider context.
So you can replicate it, or understand the system's logic.
Precisely. It's about understanding the engine itself, not just knowing where the car is going.
Okay, I think I'm starting to see the distinction clearly now. Let's make it even more concrete, though. How does this play out in the real world?
Good idea. Examples really help.
Let's take rental applications. That's a common area where AI is used, and sometimes, well, controversially.
Very relevant. We've seen reports about potential bias, data privacy issues. Things like the Landlord Tech Watch or Locked Out series highlighted these.
So imagine an AI recommends rejecting a rental applicant. What does interpretability look like for that applicant?
Okay, so for the applicant, an interpretation would give them the meaningful reason behind the rejection in context.
Like what?
Well, a human agent using the AI might interpret the system's output and tell the applicant the system flagged a lack of rental history, which we see as a financial risk.
Ah, okay, so the applicant doesn't need to know about the algorithm itself.
Not at all. They need to understand why rental history matters in this context. The interpretation gives them actionable insight. Okay, I need to build a rental history.
It gives just enough detail for them to understand the decision's impact and maybe what to do next.
Exactly. It aligns with the purpose assessing suitability and helps the human make a consequential decision.
And then the explanation in that same scenario. Who needs that and what would it look like?
The explanation would be for, say, a technical analyst or someone auditing the system.
Right.
It would detail how the rejection was calculated. For example, the algorithm is a logistic regression classifier. These are the feature weights. The applicant's score fell below threshold X, and rental history 0 was the feature with the largest negative impact.
Much more technical.
Way more technical. That analyst needs that detail maybe to check if the model is fair or if it's working as intended or if that weighting makes sense. It's about debugging the system's implementation.
Okay. The difference is stark there. One's about helping the person, the other's about checking the machine.
You got it.
Let's try another one. Medical diagnosis. Say, antibiotic prescriptions. There are similar concerns about AI bias in healthcare too, right?
Absolutely. We've seen reports on things like biased kidney transplant algorithms. So, yeah, let's use the antibiotic example. Imagine an AI suggests not prescribing antibiotics for an upper respiratory infection. Maybe it calculates only a 5 or 10% probability that it's a bacterial illness, which is usually what antibiotics treat.
So low probability. How would a doctor interpret that? Would they just automatically follow the AI?
Not necessarily. An expert physician might look at that low probability but still decide to prescribe.
Why? Based on what?
Their interpretation might draw on a broader clinical picture. Maybe a simple gist like, well, better safe than sorry with this particular patient.
Or maybe they know something specific about the patient.
Exactly. Maybe the patient is particularly vulnerable to complications, or they have a history that makes a bacterial infection more likely despite the initial symptoms. It becomes a strategic clinical choice.
So if the doctor uses their own expertise, their values, their knowledge of the patient to interpret the AI's number.
Precisely. They integrate the AI's output into their broader decision-making framework. That's interpretability in action.
So what does this really tell us then? Stepping back.
Well, it shows that interpretability aims to provide just enough detail for someone to make a meaningful, consequential decision aligned with the purpose of the task.
Right, empowering the human.
While explainability is about providing those detailed mechanisms for technical understanding, often separate from the immediate decision context. Understanding the engine, remember?
Got it. Okay, now this next part, drawing on psychology. This is where I thought it got really interesting.
Ah, yes, the fuzzy trace theory connection.
Tell us about that. How does psychology help us understand how people interact with AI explanations or interpretations?
Well, fuzzy trace theory comes from experimental psychology, and it suggests something really key. Humans don't just store information verbatim like a computer.
Okay.
We actually encode multiple levels of mental representation at the same time, in parallel.
Multiple levels, like what?
Like those gist interpretations we talked about, symbol meaningful summaries, and also precise verbatim representations, the detailed raw facts or numbers.
Yeah, and the theory says we prefer the gist.
Overwhelmingly, yes. For decision-making, humans prefer to rely on the simplest representation that gets the job done, the gist. And these aren't just random simplifications, they capture essential, meaningful distinctions.
Can you give an example of these gists in action, maybe related to evaluating AI models themselves?
Sure. Think about a data scientist looking at different models to detect, say, harmful online content. The report has an example like this in Table 1.
Okay.
Maybe one model, a k-nearest neighbor or KNN model, gets 52.4% accuracy. Now, if 50% is just random chance...
Then 52.4% is barely better than guessing.
Exactly. An expert would immediately form a categorical gist. Essentially no predictive accuracy that takes background knowledge, knowing it's a binary task, probably balanced classes.
Right, but then what if another model, say a naive Bayes one, scored only 26.7%? That sounds awful.
It does sound awful, but an expert might still give it the gist of having some accuracy.
Why?
Because they know that for some types of classifiers, like naive Bayes on certain problems, getting consistently wrong answers is actually informative. If it's wrong, most of the time in a predictable way.
You can just flip its answers.
Bingo. You flip the labels, and suddenly 26.7% accuracy becomes 73.3% accuracy. That's some useful predictive power. But recognizing that requires deep expertise. It's not just about the number, it's the meaning of the number in context.
Wow, okay. That's a great example of a categorical gist, some versus none. What about ordinal gists?
They come in when you need a bit more precision than just some or none, if several models all fall into the some accuracy category.
You need to rank them somehow.
Right. And ordinal just lets you do that. More versus less. So maybe the logistic regression model has more accuracy than the naive Bayes model, even if both have some. It's a relative comparison.
And distinct from those gists are the precise verbatim representations, the raw numbers.
Exactly. Like the actual F1 score of 0.718 or the precision score. Using these directly often involves just applying a rule learned by rote.
Like pick the highest score.
Yeah. An inexperienced student might see a support vector machine, an SVM, with a perfect precision score of 1.00 and think, that's the best.
But an expert might be suspicious.
Very suspicious. An expert modeler knows that a perfect score, especially on precision alone, could easily mean the model is overfitting to the training data, or it found some weird shortcut, a spurious correlation. It doesn't necessarily mean it's truly the best model for new, unseen data.
So experts use these insightful simplifications, these gists, focusing on the essence, rather than getting caught up in just the raw numbers.
That's the core idea. They move beyond rote application. It's like a chess grandmaster seeing patterns, not just individual pieces.
Which leads us to a really crucial point you mentioned earlier, individual differences. It sounds like what's interpretable or explainable isn't universal.
It absolutely isn't. The report stresses this. There's no single magic metric. It fundamentally depends on the user.
There's skills, their background.
Yes, their skills, their domain knowledge, their goals, maybe even personality traits related to how they process information.
And experts tend to rely more on gists.
In their domain of expertise, yes. They've learned to distill the complexity into these simple, powerful representations that guide their decisions effectively. A novice might need more verbatim detail because they haven't built up those gist representations yet.
Okay, that psychological foundation is super helpful. Now let's connect it back to the technology. How are computer scientists actually trying to build systems that provide explanations or interpretations? What are the approaches?
Right, segment 4. Bridging that gap between the psychology and the code. Computer science has developed quite a few techniques.
Many seem focused on local feature importance. What's that about?
These methods are often aimed more at developers focusing on explanation. They try to show how specific input features influenced a particular output for a single instance.
To help figure out the how for that one case?
Yeah, potentially inferring mechanisms, though usually it's more about correlation. Think LIME, local interpretable model agnostic explanations.
Right, I've seen examples of LIME. Sometimes they're surprising.
They can be. LIME builds a simpler local model to approximate the complex one just around a specific prediction. The report mentions an example, Figure 5, where LIME showed an AI focusing on the author's .edu email address or common words like have to classify a text as being about atheism instead of the actual topic words.
Not exactly a deep understanding of atheism there.
Not at all. Or that famous example in Figure 6, the husky classified as a wolf just because there was snow in the picture.
Small f.
Yeah.
Yeah, the snow wolf logic. It really shows the model taking shortcuts, doesn't it?
It does. LIME is great for highlighting these spurious correlations, helping developers debug, but it's a local approximation, remember?
And SAP is similar, Shapley additive explanations.
Similar goal, yeah. SHP, shown in Figure 7, also assigns importance scores to features for a specific prediction, telling you how much each feature pushed the prediction higher or lower, kind of like coefficients in a regression model.
But still prone to finding those spurious correlations and not necessarily showing true cause and effect.
Correct. Both LIME and SHP are powerful for debugging and understanding feature influence, but they don't automatically give you causal mechanisms. And then for images, there's GradCam.
GradCam.
Figure 8 in the report shows this. For computer vision tasks, it creates heat maps showing which parts of an image were most important for the AI's classification, like highlighting the dog's face when it classifies the image as dog.
Okay, so those are tools mainly for developers trying to understand the how. What about approaches that aim for interpretability from the start?
Right. So another strategy is to design models that are inherently simpler, more transparent.
Instead of trying to explain a black box, build a glass box.
Kind of, yeah. For example, scalable Bayesian rule lists, or SBRL. These models explicitly trade off some predictive accuracy for human understanding.
How do they work?
They generate a list of simple if-then rules with associated probabilities. The report has a customer churn example in Table 2, like if contract 1 year in streaming movies, yes, then probability of churn equal zero point 0.2. Very direct.
That seems quite interpretable, at least for someone who understands probabilities. What about GA2Ms? Generalized additive models with pairwise interactions.
GA2Ms are interesting. They model the effect of each feature independently and add effects for specific pairs of features. They can sometimes surface really counterintuitive findings.
Like the example in the report, Figure 9, about pneumonia readmission risk.
Exactly. The GA2M found that having asthma actually decreased the risk of readmission for pneumonia patients.
Which seems totally backward.
Right. But the model just shows the pattern. It takes human experts to then interpret why that might be happening. In this case, the hypothesis was that asthmatic pneumonia patients get much more aggressive care, may be admitted to ICU sooner, which ultimately lowers their readmission risk.
So the model finds the correlation, but humans still need to provide the causal story or the contextual meaning.
Often, yes, and that highlights a limitation. Many of these interpretable models are still showing correlations, not guaranteed causation. Users can easily misinterpret correlation as causation. That's a persistent risk.
Okay, so we have explanation tools for developers and inherently simpler models. What about interfaces for end users?
That's another key area focusing on interpretability. Purpose-built graphical user interfaces, or GUIs.
Like Google's What If tool.
Exactly like that. These tools aim to help users, even those without deep statistical knowledge, explore model behavior and sort of get the gist of how inputs relate to outputs. Maybe see how changing one factor might change the outcome.
But the key is context.
Right. Absolutely. The graphical output isn't inherently interpretable on its own. It needs to be presented within the user's context, aligned with their goals, and ideally combined with their background knowledge to become truly meaningful.
And quickly, what about topic models for text, like LDA?
Right. Latent Dirichlet allocation, LDA, and similar models. They analyze large amounts of text and infer underlying topics, usually presented as lists of co-occurring words. Figure 10 shows an example.
So the AI suggests the topics.
Yes, it groups the words, but then a human still needs to look at those word lists and interpret what that topic actually means. Is this topic about sports or business contracts? The AI provides the structure, the human provides the semantic meaning.
Okay, so we have all these different approaches, from developer tools to user interfaces. How do we pull this all together? How do we actually design systems that effectively integrate this psychological understanding?
Yeah, that's the crux of segment 5. It really comes down to choosing the right level of abstraction when communicating what the system is doing. Yeah, how much detail do you provide? And that choice depends entirely on the user and their needs. Are they asking how or why?
This links back to that construal level theory you mentioned.
It does. CLT suggests that how questions lead to thinking about concrete, detailed, psychologically close aspects. That aligns with explanation.
And why questions?
Why questions make us think more abstractly about purpose and goals, things that are psychologically distant. That aligns with interpretation.
And interestingly, the report notes that thinking more abstractly, using those just interpretations, can actually lead to better decisions sometimes.
It seems counterintuitive, but yes, too much nitty-gritty detail, too much verbatim information can sometimes obscure the bigger picture, the essential meaning needed for a good decision. Gists cut through the noise.
Can you walk us through that abstraction hierarchy using the loan recommendation example again, figure 11 in the report?
Sure. At the lowest level, you might have an explanation focusing on how a specific component, like a deep neural network, was physically implemented, the code, the hardware. Very concrete how.
Okay.
Moving up, you might explain its general function, how it processes inputs to outputs. Still pretty technical.
Then interpretation starts coming in.
Right. At a higher level, you interpret the functional purpose. This part of the system determines the credit score based on these factors, or this module makes the final loan recommendation. This answers why that component exists in the system.
So each level provides context for the one below it.
Exactly. The lower level explains how the higher level function is technically achieved. The higher level explains why the lower level exists. You need to pick the right level for your user.
And this sounds a lot like good practice in requirements engineering, doesn't it? Focusing on what the system needs to do, not necessarily the specific how at first.
It aligns perfectly. Good requirements engineering focuses on solution-neutral requirements,
Listening.
meaning you define what the system must achieve, say a classification accuracy of 0.85, without initially dictating how it must achieve it, like specifying it must use a neural network versus a decision tree.
Because the functional goal and its meaning for the user is often more important, especially when thinking about legal or ethical requirements.
Precisely. It forces you to think about the end user's goals and how you'll measure success in a way that's meaningful to them. It connects the technical implementation back to the human purpose.
It's really about designing for human understanding from the start, not just bolting on an explanation tool at the end.
That's the ideal, yes. And it often requires bringing together different kinds of expertise, not just AI developers, but systems engineers, domain experts, user interface designers, psychologists, potentially, to make sure the final system truly meets the needs of its users.
Wow, this has been, well, incredibly clarifying for me. I feel like I have a much better handle on this now.
Good.
So just to recap the core message from NIST 8367, explainability is the how it works, mostly for technical folks doing debugging or improvement.
Right, the internal mechanisms.
And interpretability is the what it means, giving end users the context and meaning they need to make good decisions.
Exactly, deriving that meaningful gist.
And crucially, it's not one size fits all.
Yeah.
It depends on the user, their background, their goals. You tailor the level of detail.
Couldn't have said it better. Understanding the psychology, how people actually make sense of information, especially through these gist representations, is vital if we want to design AI that people can trust and use effectively.
And, this whole discussion really highlights something profound, I think. The report touches on this idea that AI systems, like human experts sometimes, can get the right answers, but maybe for the wrong reasons.
That's a fascinating parallel.
Think about it. A brilliant, experienced doctor might have an intuition, a correct gut feeling about a diagnosis, but they might struggle to articulate every single step in their reasoning perfectly.
They operate on those expert gists.
And complex AI models can do something similar, right? They find patterns, correlations, arrive at accurate predictions, but maybe through pathways that aren't easily explainable or even based on the factors we'd expect.
It happens all the time. The husky in the snow is a perfect example. Right answer. Husky, close enough maybe. Totally wrong reason. Snow.
So that leaves us, and you listening, with a really big question to think about. As AI gets more and more sophisticated, maybe even more opaque in some ways, how much of the how it works, the deep explanation, do we actually need?
Versus how much what it means, the interpretation, is sufficient.
Exactly. How much why versus how much what it means do we need to foster trust, ensure accountability, and just live effectively in this world that's increasingly driven by AI decisions?
That's the multi-billion-dollar question, isn't it? Finding that right balance for different contexts.
Something to definitely ponder.